In the previous section, we looked at combinations of functions, how to make a new function from two or more other functions. One of those combinations of functions was called the composition of functions, f composed with g or g composed with f. And we'll use that composition of functions in this section to prove whether or not two functions are inverse functions of each other. Well, let's start off by, in this section on inverse functions, let's start off by an informal definition. If a function f undoes what a function g does to a number x, and vice versa, then the functions f and g are inverses of each other. Now that's a very informal definition, but let's look at a real simple example. We'll probably look at this same example in a few minutes, but if one function takes in a number and adds 10 to it, then the inverse function would be a function that takes in a number and subtracts 10 from it. Now that's a very, very simple example, and we'll be working with more difficult functions than that, but let's continue with inverses. All right, definition. If functions f and g are such that these two things hold, f of g of x, remember that's the composition of functions, that's f composed with g of x. This is the definition of f composed with g. If that's just equal to x, and then when you reverse it and you say and g of f of x is also equal to x, then g is the inverse function of f. And it's denoted like this. It looks like f to the -1 exponent, but if it's a function, you're talking about an inverse function. So what this says is g actually is, we could call g f inverse. And I could have chosen it the other way around. I could have said f is the inverse of g, which it would be, and then we could denote f as g inverse. So either way. But in this case, we have the following. F composed with f inverse of x. So f of f inverse of x is equal to x, and f inverse of x is also equal to x. So what's really happening? You're taking a number, call it x, you're applying the function g to it, and then whatever you get out, g of x, you're plugging it into the function f, and the result is the exact same thing that you put in. Okay, so domains and ranges. Let me just draw a little picture to describe this one. The domains and ranges of f and f inverse. So suppose we have f and f inverse. And let's just call these are two sets of numbers. And the function f takes these numbers and maps it into these numbers. Okay, so this would be the x values of f. So this would be the domain, maybe I'll just use the symbol, capital D of f. Obviously, this is the domain. F operates on these numbers and you end up in the range of f. I'll make it a capital R, subscript f. Okay, well, f inverse starts with these numbers and maps them back to here. So f inverse could be going this direction. So what's another way of saying the range of f? It's the domain of this function. Equals, that's a sideways equals, the domain of f inverse. And this would be, the f inverse starts with these numbers, and you apply this f inverse function and it puts you right into this, which was also called the domain of f. Well, it's the range of f inverse. And again, those two things are equal to each other. So you could just simply say that the domain of one of them is the range of the other, and the range of one of them is the domain of the other, just like we have pictured here. So if we were to take one example, let's say that's A, that's the number A, then f of A would be this say this number right here, that would be f of a. Then if we take f of a, whatever that number is, and plug it into f inverse, it's going to take us right back to where we started. So f of f inverse of a is a. And maybe I'll just put a f inverse of a would be that point right there. Okay? Okay, it's kind of a messy picture. Let's move on. Okay, last couple of examples here in this video. I bet you know the answer to this before we even prove it, but we need to mathematically prove it. Are these two functions inverses of each other? Notice what this one does. If you plug in x, it spits out 15 more than x, so it adds 15 to a number. This function g subtracts 15 from a number. So I suspect they are truly going to be inverses, and we'll address the domains and ranges at the end. Okay, f of g of x. That means we input g of x into the function f. So here's the function f. If I replace x with g of x, I'm going to get g of x plus 15. Now let's simplify that. G of x is x minus 15. And plus 15. And sure enough, we got x. And let's do it the other direction. If we plug f of x into g, that means we're going to get f of x minus 15. We're just replacing this x with f of x. And that gives us x plus 15, because that's f of x, minus 15, which is also x. So yes, indeed, they are inverse functions of each other. And as you might imagine, if I took x plus 100 and x minus 100, those would be inverses of each other as well. Okay, so what are the domains and ranges? This is so easy. Recall from the previous section, we're dealing with functions that if there is no division, you can't have a division by 0. So there's no problem numbers due to that. There's no radical. So we don't have to worry about getting a negative under a radical. So the domain of both of these would be all real numbers. And now that we know they're inverse functions, we know that their ranges are all real numbers as well. And why is that? The domain of this one is equal to the range of this one, because they're inverse functions. The domain of this one is equal to the range of this one. Since they both have domain all real numbers, they'll also have ranges of all real numbers. So in conclusion, because of this, we can simply say that f and g are inverse functions. And I'm going to state that another way. And g is equal to f inverse, and f is equal to g inverse. So whichever letter you prefer, you could stick with that. We could call g f inverse, so then we just have this is f, and this is also f inverse. So g is f inverse. Or if you like g better, you can say g is equal to x minus 15, and the function g inverse is x plus 15.